All right. Anytime we're told that something grows at a rate proportional to its size, that means that we can use the law of uninhibited exponential growth to mathematically model the situation. So the law of exponential growth, the law of uninhibited exponential growth is expressed as b equals b sub 0 e to the kt. Oftentimes, by default, it'll be the letter P will be used, but I'm going to use B's since this is representing the number of bacteria. Um, B sub 0 is the number of bacteria there were initially, and it looks like initially there were 6,000 bacteria. That's at 10 a.m. So at 10 a.m., um, which that's going to be at the start, at t equals 0. We're told that there are 6,000 of these things. There's 6,000 bacteria. By noon, at 2 hours later, so at t equals 2, we're told that there's 6,600. So b of 2, this up here is b of 0. B of 0 is equal to p sub 0. That's how much there were initially. But in 2 hours of b of 2, that we know that the bacteria grew by 600. And the goal of this thing is to figure out how many bacteria there will be at midnight. Now midnight is actually 14 hours later after 10 a.m. So the goal of this problem is to figure out what b of 14 is. Okay, but to figure out what b of 14 is, in other words, the number of bacteria at midnight, we have to in order to utilize this, in order to use the law that I have written here, there's two things we need. We need b sub 0, which of course they basically gave me. I'll go ahead and plug that in. B sub 0 is 6,000. But in order to utilize this formula, in other words, in order to answer the question, b of 14, we need to figure out what k is. So the bulk of the work here is going to be finding the value of k. So to find the value of k, we're gonna plug in the knowledge that we know. We know that if we plug a 2 in for t, b will end up being 6,600. So b is 6,600 if t is 2. Now we're going to solve this for e. I'm sorry, we're going to solve it for k. Now to solve an equation with an e in it, that has an e on one side and not the other, we're eventually going to natural log both sides. But we can't natural log until the coefficient is equal to 1. So to get rid of that 6,000, we'll divide both sides by 6,000. And now we can natural log both sides. And I'm going to go ahead and reduce 6,600 over 6,000, that, that can be reduced to 66 over 60 easily, which, of course, that fraction can even be reduced by another factor. We can reduce again. So I reduced it a little bit. So I noticed that I natural logged the left side, but I failed to natural log the right side. And I need to put a natural log right here. So going from this step to this step, we natural log both sides. And the reason why we natural log both sides is because the natural log and the e cancel out, so we're left with 2k. And on the left side, we have natural log of 66 over 60, which I'll go ahead and reduce again. 6 goes into both of those numbers, so I can divide both numbers by 6, reducing it to 11/10. And to solve for k, we would finally divide by 2. But to avoid the complex fraction, I would prefer that we multiply both sides by 1/2. Multiplying by 1/2 is the same thing as dividing by 2, but it avoids the complex fraction. And so there's k. Now we need to take k and plug it back in right there into our formula. So doing so gives me b equals 6,000 e to the k, which is 1/2 natural log 11/10 natural log 11/10 times the t. And so the next thing I'll do is multiply the t and the 1/2 together. What I'm doing now is starting to simplify this formula. Eventually I'm going to rewrite some things so I can get rid of the e and natural log. They'll cancel out. So multiplying the 1/2 and t gives me t over 2. And what that does is it allows me to take this number and put it in the exponential spot using the power property of the logarithm. So I have e to the natural log of 11/10 raised to the t over 2 power. And now at this time the e and the natural log cancel each other out. So we have b equals 6,000. E and natural log cancel out, so we have 11/10 raised to the t over 2 power. At this time I now have a beautiful formula that I can use to figure out the number of bacteria at any time I want. We want to know how many bacteria there are in 14 hours at midnight. So we're almost done with this problem. The last thing we do is just plug a 14 in. So we're going to have 6,000 times 11 over 10. And if I plug a 14 in for t, 14 over 2, I'll go ahead and put a 7 right there, right? So I just plugged a 14 in for the t, and I went ahead and divided it by the 2, and so that's where I got the 7. And this is where I need to pick up the calculator. So in my calculator, I'm going to type in parentheses 11 divided by 10, and then I'm going to raise it to the 7th power. So in my calculator, it looks like this. On my calculator screen, I have a parentheses 11 over 10, and then I use my exponent button, and I raise it to the 7th power, and I got 1.9487171. But now I have to multiply that by 6,000. So using my calculator, I multiplied it by 6,000. And back up here, they want me to round to the nearest whole number. And so the nearest whole number is 11692. My calculator says 0.3026, but this is to the nearest whole number. That's how many bacteria there's going to be at midnight.